Network performance directly dictates business performance. For resilient enterprises, the difference between failure and scale comes down to mastering two distinct levels of infrastructure: global routing at layer 3 and local quality control at layer 4. This chart maps the OSI reference model against the TCP/IP model. These frameworks structure all enterprise communications. Layer 3 access the global logistics network, handling IP addressing and routing packets across environments. Meanwhile, Layer 4 is the quality assurance manager, overseeing end-to-end delivery. At the core of Layer 3 is the Internet Protocol, or IP. It is a connectionless, best-effort utility that routes traffic without setting up a dedicated path, treating every data packet separately as it travels. For decades, networks relied on IPv4. This 32-bit architecture provided roughly 4.3 billion addresses. Today, that capacity is completely depleted. To keep the Internet functional, network engineers use network address translation and port address translation. These protocols map internal private addresses to a single public IP, artificially extending IPv4's lifespan, but creating complex translation bottlenecks. The migration standard is IPv6, which replaces the 32-bit limit with an expansive 128-bit architecture, providing a nearly infinite address space. Upgrading to IPv6 is a mandatory infrastructural shift. Enterprises must make this transition to scale globally without relying on inefficient, congested workarounds. Regardless of the IP version, routers face a core requirement: to physically deliver data across a local network segment. Logical IP addresses must be accurately translated into physical hardware addresses. In an IPv4 framework, the Dynamic Host Configuration Protocol automates IP allocation. Then, the Address Resolution Protocol, or ARP, links that logical IP address to a physical Layer 2 MAC address on the device. When an enterprise upgrades to an IPv6 framework, the underlying mechanics change. The Neighbor Discovery Protocol directly replaces ARP to handle all physical address translation. Once Layer 3 handles the routing, Layer 4 takes over. Here, selecting the correct transport protocol dictates whether an application functions smoothly or fails under pressure. The first option is the Transmission Control Protocol, or TCP. It is a connection-oriented standard that guarantees data delivery by establishing a strict three-way handshake and managing flow and error control. This built-in reliability makes TCP mandatory for high-stakes transmissions, where missing data is unacceptable, specifically emails and large file transfers. Alternatively, the User Datagram Protocol, or UDP, operates as a connectionless standard. It strips away handshakes, acknowledgements, and delivery guarantees in exchange for raw transmission speed. UDP's speed is explicitly designed for real-time applications. In voice-over IP and video conferencing, dropping a single frame is highly preferable to delaying the entire communication stream waiting for a retransmission. Look at your enterprise network. Evaluate if your architecture leverages the correct mix of TCP guarantees and UDP speed for maximum performance. Align strategy, optimize the network. Until next time, keep business connected, your assets visible, and your infrastructure secure.